mathematics and lines. It includes art and nature.
We are going to talk about straight lines made by human beings. And I just love this picture of this little boy because it says so much. He is, this is Egyptian. The idea is, well, it's obviously modern, but it's portraying the idea. He's saying, I got it. And what he's got is a right angle. And he has got a right angle because what he has got there is a 3, 4, 5 triangle. And that, at that time, people knew about Pythagoras' theorem. And they knew that for certain, if the square on the hypotenuse, 5 squared 25, was 3 squared plus 4 squared, which it is, then the angle where his hand is holding it, the rope against the vertical brick wall and the ground, will be a right angle. So that's how, for centuries, millennia, people have made right angles. And why are right angles, indeed, why are straight lines important? Well, you see that in the middle picture. We'll come back to the little boy, but you can see from the middle picture, Caroline, you're the engineer. Why are straight lines important?
Well, straight lines are important in buildings, in structure, because to give it strength. I mean, curved lines are fine on roofs and things, but if you've got load bearing, it has to be rigid. So if you want to put a weight on top of something, it will hold it. If it's rigid and straight, it will hold it. But if you bend it, it will collapse. So it has a lot more strength if it's straight and rigid.
Yes, and we might have drawn a picture of a bridge with all those, braces that what gives the bridge its strength being straight. And that is, by the way, Dubai. I thought that was a nice contrast. The little boy's foot is pointing to this very modern city, which has been built in the last 50 years. But yes, there's another thought I have about straight lines. If you draw a floor plan of a house or something, if your angles at the corner are not 90 degrees and your lines are not straight, not only will your walls likely fall down for the reasons Caroline has given, but then when you draw the fourth line, it won't meet up with the corner that you started with. You're
going to either have a diverging lines or converging lines. So they're either going to meet up too soon or just never, ever, ever meet up.
Yeah. And you might deliberately make your room other than rectangular, but usually most of the rooms are rectangular, which comes to the picture. I thought those two cities juxtaposition was rather nice. You've got New York, a city plan rather, a street plan of New York with the streets and the avenues. And you have got, that was planned hundreds of years ago. But you have got the modern city of Dubai, which is super modern. And along the front there, the more sort of conventional Western style buildings in one of the suburbs of Dubai. I mean, Dubai is an amazing place. Have you ever been there, Caroline?
No, I haven't had the pleasure yet.
Well, it is. I mean, in some ways, it is. Well, in some ways, it's perhaps a bit sad that the wonderful Arab people who lived in their communities in the desert, in tents, have now moved into the modern world. But in another way, it's quite spectacular. And when I was there, I walked into the center of the very, very old part of Dubai and street markets and things. And that was another world, very different from the ones you see in that picture. So to go back to New York before we leave it, there the streets and the avenues are perpendicular, and they are all of them more or less straight. It's a sort of grid plan, as are
American blocks. When they talk about a block in the States, it usually is straight, at least in the cities. Not so much the suburbs, but in the cities it definitely is. And there's such a contrast to the old country in where I live in England. You don't see straight.
No.
Where you are in Cambridge, you just don't see straight streets.
No, I mean the
good old Roman roads.
Yeah, yeah, yes, they had and of course that was their idea of the straight line being the shortest distance between 2 points, which we'll come back to later in this program. But there's a couple of other things before we move on that I'd like to mention about. First of all, about the buoy and the right angle. You can see there that the ship's mast and is a straight line. It's got to be straight because, again, it's got to hold up the sail, and for the reasons Caroline gave, it must be straight. And then you have got also what I thought was quite interesting, just a coincidence really, that the straps on the boy's sandals, some of those are straight too, aren't they? Where they go around his ankle. I mean, the interesting thing about straight lines is when you take a wrapper off a can, like a can of Heinz beans or something, if you take the wrapper off, you can flatten it. And although it's a circle round the can and that strap around the boy's ankle is a circle, when you flatten it out, if you flattened it out, it would be straight. A straight line in the sense we usually think of as straight lines.
Yeah.
What about the pyramids at Giza? Isn't that a lovely picture?
It certainly is, and it actually also reminded me, oh dear, the name just came to me, that the architect in Barcelona that makes all the curvy lines is actually a lot harder to make a strong structure out of curves than it is to make a strong structure out of straight lines. So he was actually quite clever because he managed to do it. But the logical thing, and the thing that they could do and they could repeatedly do, and is make the straight edges. Although if you get up close, of course, they're not actually lines, they're made up of big blocks, but they make up a straight line.
Yes, well, I mean, the sort of overall is straight, but they are sort of steps, aren't they? Yes.
But again, that is extraordinary, the engineering of it, that they actually managed to create these blocks how many 4,000 years ago, and effectively make these really straight lines. If you average it out, they're nice shapes, and it's to me it always boggles my mind at just how amazing engineers are. I'm not a structural engineer, and I'm not an architect, and it really astonishes me every time I look at any structure. People actually succeed in building it and building it accurately.
And what about the cooling tower? Isn't that fantastic? Now, if you look, you can see some straight lines there, and in fact, the cooling tower shape it is made up entirely. It's a ruled surface, in fact, and it is made up entirely of straight lines. So if you imagine infinitely many straight lines, as you see, like the ones you see drawn, but sort of going all the way around, there you have a cooling tower. We see cooling towers in our countryside, and here you see the waist, or weight. If it was a human, he might put his belt. Okay, if you do draw the lines more vertical than those, then the waist is thicker. So your cooling tower is less of a shape where it's pushed in. And what you see, where you see through the sides, those are hyperbola. So the white space behind the two edges, or the two curved edges there, are hyperbolas.
Okay, so what you're saying is, in the extreme, if you made them those lines completely vertical, you basically have a cylinder.
Yes.
Would that be correct? And
yes.
then by turning the line, by angling them more and more, you're creating a hyperbolous shape that's causing the waste. And then the more angled those lines are, the narrower the waist. Is the extreme going to be that it's flat and it's a circle?
Yes, yes, a cylinder, and then yes, and interesting. I hadn't thought of the sort of dynamic view of that, Caroline. How interesting. Okay, well, we need to move on, and this is straight lines in nature.
Daffodils, my favourite. It's my favourite flower.
Well, when Caroline and I first talked about doing this hour, we thought, oh, there aren't many straight lines in nature. And then I had to think again about it. Caroline suggested the honeycomb, and there it's the wax. Of course, it's a packing of hexagons, and it's the wax that's forming straight lines. Ooh. Although if you look very closely, they're sort of a little bit wobbly straight lines. And
no one's perfect.
The same can be said of the spider's web. I mean, they are more or less straight lines, but not perfect straight lines.
Well, I tell you when they are, though, Toni, is where the ones in between. I mean, you can see there's ones that are curvy, but you can have really, really straight lines if there's no weight on them. Super straight lines. If it's just one line where when it comes down vertically, you've got straight lines there. The spiders can create straight lines. It's just that other forces come to play and influence the shape. But the spider can make a straight line.
and Caroline mentioned the daffodils. Lovely, aren't they? They're in bud there, and very soon we'll have our daffodils in England. They're not quite out yet. Maybe people have seen the first daffodils. And above that picture of daffodils, there's ice on a little pond there. Now that's been a man-made pond, but what I think is so interesting is about the cracks in the ice. I mean, we in this country, well, people my age anyway, are used to seeing frost on the window in the days before central heating. That's a similar sort of phenomenon, isn't it? I think that's
that's actually another point, because you've got crystals, of course, that make straight lines, and of course frost on windows that gives you straight lines as well. But this is extraordinary. I've never seen anything like it. You've got lots of triangles, all kinds of triangles.
Isn't it brilliant?
Different. It's amazing. I want to make that happen. How do I make that happen?
You can experiment, Caroline. You want to put dishes of water out when you have to do it soon, because these overnight frosts, will soon be past them, or will soon be into spring. And of course,
I've never seen it. Yeah, go on.
On the right, top right, you've got the palm fronds. Isn't that beautiful?
Yeah.
And on the bottom left, you've got an avenue of, I think they're silver birches, which are quite beautiful, I think. Somebody's planted them in straight lines, but they do grow up more or less straight, don't they?
Well, I mean, even the masts in boats, these days, they don't tend to be wood, but there was a time when they were all wood, and they had to come from really straight, strong hardwood trees. There was no... Yes. So, yeah, trees make straight lines. Yes. If you just chop off a little small part of a branch, a little twig, that can be a lovely straight line. Great straight lines in nature, all over the place.
And I haven't got a picture of one, but I heard that you can grow a walking stick. I heard it in Gardener's Question Time yesterday, that there's a plant that's called the walking stick plant, and it grows so straight that people actually, and it is wood, sort of, I think. It grows very fast. And you can grow your own walking stick. So why don't you plant a walking stick, Caroline? So, but by the time you need it, it'll be ready for you to cut and use.
Sounds like an excellent idea. Can I plant it in your garden?
And the other only picture we haven't talked about is Fingal's cave there. And isn't that beautiful? I went there on a boat, and oh, it's just mind-blowing. They do take boats into the cave too. It's a bit dark, you can't actually see the cave very well in the photo. But those basalt, I think they are, columns, are natural, of course, and they actually make one think of crystals in nature, of course, because crystals are the edges of them are always straight and nearly, and that's another straight structure in nature. And then you mentioned Giant's Causeway, Caroline.
So just across the water, where Fingal's Cave is in Scotland, which is actually quite close to Northern Ireland, there's a place in Northern Ireland that's got lots of hexagons, just like a honeycomb. And the rocks, because of frost and because of the type of rock itself, because of water getting in and freezing and then opening up, just make lots and lots of hexagons. It looks like a honeycomb. And there's a myth, legend has it, that Northern Ireland was once home to a giant named Finn McCool. That's the English way of saying his name. And there was another giant, Benandonna, across the Irish Sea in Scotland. So he would have been in your cave. And now Benandonna, threatened Ireland. So Finn retaliated by tearing up great chunks and hurling them into the sea, and basically somehow destroyed the connection between the two lands, and so that Benandonna couldn't come and threaten Northern Ireland. And
so that's why it's called a causeway, of course. Yes, yes. And oh well, I wonder if Finn knows that story. One of my grandsons is called Finn.
Can I tell the joke?
Please do.
Right. I ordered a takeaway from the local Chinese last night. I ordered a 23, a 13, a 31, and a 79. But I had
What's
to take
funny
it
about
back.
that?
What's funny, I had to take it back. It tasted a little bit odd.
Well, straight lines that are actually curved, or curved lines that are actually straight. Now here, I have selected a few pictures that show a sort of link between maths and art. And what you see just below in the bottom half, just towards the right, you'll see somebody's hands and a grid lines, and you'll see how these pictures are actually drawn. What you've got is straight lines, but the edges of those straight lines make what appears to be a curve. And the mathematical word for that is an envelope, not the sort of thing that you put a letter in and then lick the flap and put it in the post box, but not that sort of envelope, but this is a mathematical envelope. And here you have some wonderful pictures made in that fashion. And first of all, the amazing picture up on the top of Anthony Hopkins. Did you recognize him?
I did, most definitely. He looks like Hannibal the Cannibal.
And look closely. Can you see the straight lines?
I can see the straight lines. He's actually made, you can't see it so much on the facial features, but you can definitely see it on his shoulder, his ears, below his chin, and it's all made of straight lines. It's amazing.
Now, isn't it? I mean, that's real art. Now, if you
this is where maths and art, I mean, this is a really obvious place where maths and art come together, because you can make art using geometry, basically.
Well, I think, there's a lot of art in what you see on here. I mean, the one below Anthony Hopkins, what has happened there is the artist there has played with this idea, and in a lot of different ways, and sort of put them together, considering, carefully how he assembled the different designs. And I think that's really striking.
Yes.
Some of these straight lines are not actually straight. I think they're drawn freehand, especially the tree.
Yeah, the tree you can see very clearly some of the lines are curved, but other ones, they really look curved. And if you look very closely, they're really not, like the one to the right of the tree. But I think they are freehand. I'd agree with you there. But
some of them are forming...
That's not very done very precisely, but I think they are all straight lines.
But some of them are freehand, but some of them are actually part of an envelope, just as you see in the other diagrams. The one on the top right extreme is definitely all carefully drawn straight lines. The one next to it, which is rather similar, I'm not sure whether that's free drawing or whether it's just the resolution in the picture that makes it look a bit as if the lines are not quite straight. So we have got quite a few different examples here. Now, if you go to the link that's shown there to the Aiming High website, and you go to this construct circle and line patterns,
it is in the description.
You'll find there are not just one, there's many, many, many different activities that help you to draw similar patterns to what you see here. Now, the difference...
This is a great activity for a child who wants to do something, you want them to do something educational. Well, this is an activity that they can do, that they can love doing, and at the same time, it's edifying.
It's maths and art, and there's a lot of maths in it, but for people who like to do things that with art, it's great fun. And the bottom right there, there's a bit exceptional to the rest. It's certainly maths and art, straight lines in art, but somebody there has been experimenting with the idea of perspective and drawing straight lines, and they're cuboids, but you see them in all sorts of different ways if you keep looking. Very clever, that one. Remember what we're talking about. This is curved lines that may be straight. And what you see on the top right there, oh no, just the right, is air routes from Europe to Indonesia and to the east, and air routes from Europe to North America. And I think it shows you very clearly how some of those air routes between Europe and, say, Canada, and even going to New York, actually go up towards the North Pole. They go up towards Greenland. That seems a bit odd to some people, to be on a flight from London to New York that takes you up over Greenland, Hudson Bay and the like. So why am I saying that these lines are curved lines that are actually straight?
Because the flatlanders are wrong. The world is actually spherical.
Yes, that's true. But a bit more, that is true, but a bit more than that. The point is the air routes are the lines of shortest distance. And that is really what a straight line is. It is a line of shortest distance. And even if I'd shown you that on those airlines on a globe, you'd still have to agree that they were circles, okay? So you can have a circle that's actually a straight line if it's on a globe, or if it's just above the globe, if it's an airline. Isn't that
right?
So
a line goes from A to B and it doesn't wobble, it just goes straight from A to B, and the shortest possible line is a straight line, even though it's curved, because it's on the surface of the sphere or whatever surface it's on.
And on the globe, a straight line is a great circle, and everybody knows about the great circle, the one obvious one, which is the equator, and all the lines of longitude are great circles. Actually, the plane through them cuts the globe in half, but there are many more great circles. In fact, between any 2 points, there's a great circle. So if you were to go from, say, somewhere in Indonesia...
Well, any 2 points form part of a great circle.
Yes, it's on a great circle. So if you were
On
to
a great
go from,
circle, yeah.
if we were to go from Indonesia, say to Mexico, the air route would take you on a great circle, and if you went all the way around the globe, this would be a complete great circle around the globe. But it doesn't go through the North Pole.
Keep going in a straight line, and yeah, you will end up back in Indonesia and have traversed a great circle. Nice.
And on the left, you've got what is called stereographic projection. Now, this explains mathematically how the points on the surface of a sphere can be projected onto the flat horizontal plane in black, as you see it. Okay. So you see all the lines are from the North Pole, and they all go down inside the sphere as chords, if you like, and they pop out of the sphere, and then they carry on straight, and they hit the plane, the black surface. And you see that on the right, a circle, which you see has spokes of a wheel, that one. When you see its image, it's only showing you 3 points, but the image of that circle is a circle on the plane. It doesn't actually show you the image of the spokes, but you can imagine those. The other circle appears a straight line. So circles through the North Pole come out as straight lines. And you see the two little curves, which are actually parts of great circles on the sphere. And you see them projected on the plane. And you put tangents between to each of those lines. The angle between the tangents, alpha, is preserved. So it's an angle preserving map. Angles between lines are the same, whether you see them in the projection, as in the map on the right, or whether you see them actually on the surface of the sphere.
Toni was going to cover one of my absolute favorites. Is he an artist? Is he a mathematician? What is he? He's just amazing.
Escher. Now, Escher, we should do a whole program on Escher, Caroline.
Let's Toni, let's.
But here you see his 3 geometries. Now, he started off doing very, very geometrical art. And then I think, I'm not sure who contacted whom, but Coxeter in Canada, who is a very, very well-known geometer, and Escher got together. And my husband and I knew Coxeter quite well. And he told us that he learned quite a lot from Escher, and Escher learned quite a lot from him. Isn't that marvelous? So Escher's ability to visualize saw things in geometry. And of course, Coxeter spent his whole life studying geometry, first in England, and he was a student here in Cambridge, and then in Toronto. So here we have Escher, 3 pictures showing 3 geometries, and we've got some more slides, and we're going to talk about spherical geometry, Euclidean geometry, and hyperbolic geometry, and the difference between them. And here you have a tessellation of angels and devils. So look at them. Aren't the devils frightening? And aren't the angels beautiful? Okay. And I think that woodcut on the left, it's a woodcut. Isn't that beautiful?
It's amazing.
It's a ball, it's a sphere, and it's a tessellation just like the one in the middle. Now, the one in the middle is Euclidean geometry, which people learn at school. And the majority of people really think there is only one geometry. And of course, that's because that's the only one they've learned about. But the other geometries are just as important. And it was really Einstein who woke everybody up to the fact that the curvature of space, okay, and how important this is to us all. And he was taking us into the realm of the geometry on the right, which is hyperbolic geometry. And there, one model for hyperbolic geometry is what we call the unit disk. And would you believe it, that all those angels and devils in the geometry on the right are the same size? Now, they don't look the same size. I'm sorry, they don't, but that's because we have got Euclidean eyes. And because we're used to inhabiting a Euclidean space, and somehow we're not big enough or small enough, I'm not sure, to be able to view the angels and devils in hyperbolic space and to understand that they're all the same size. But there's an excuse, actually, for us, and that is that distance is defined differently in hyperbolic space.
Okay.
And of course, we can't do justice to it in a few minutes, because some people spend their whole lives devoted to hyperbolic geometry and all the ways and different ways it can be applied. And some people think it's very pure, and oh my goodness, you know, why would a mathematician want to study it? It's very pretty, but is it useful? Well, I assure you that hyperbolic geometry is very useful. Not only did Einstein tell us in the theory of relativity how useful it was in studying the universe, but there are many, many other applications. So that, I think, is wonderful. Now here we have an illustration of the three geometries. And the difference,
there's the hyperbolic, yeah.
The difference between them. And you can see on the left, Euclidean geometry. And we all learn that the angles of a triangle add up to 2 right angles, don't we? Yes, but do they? Well, the answer is, the answer is no. The answer is, well, yes and no. It depends on which geometry you are in, okay? So let's go to spherical geometry, because in reality, that's where we live. I mean, you know, as Caroline said earlier, we're not flatlanders, are we? Okay, and those red lines on the sphere you see there, they're great circles. And they're the straight lines of that geometry. And does it look like the angles add up to 180 degrees or 2 right angles? No.
No.
The angles add up to more than 2 right angles. Wow. Okay, so another non-Euclidean geometry is the hyperbolic. And there you see a triangle. This is a different model. This is the hyperboloid model, and it's like the cooling tower, okay? So this is a model of hyperbolic geometry. And in the geometry, you can have either that model or you can have the unit circle model. They're both equivalent. You can go from one to the other, and everything that you can describe in one is exactly, you can describe it, you know, absolutely, you know, word for word, bit for bit, exactly the same in both. But here's the hyperbolic model. The triangle there, do the angles of the triangle add up to less than 2 right angles, exactly 2 right angles as in Euclidean geometry, or more than 2 right angles?
And this is studying it theoretically might not sound terribly relevant, but these occur in real life. You've got these saddles between 2 mountains, exactly that shape, where they go up and join in the middle, and then they go down on either side. Even we've got it on our hand as well. Alan was showing it, wasn't it? We've got it between our thumb in that that section there of the hand. You've got this up and down and sinking in between. It's a very real, it's a shape that we encounter in our lives.
Banana.
A banana. Oh, there you go. A banana. Yes, a banana.
And you see the triangle there, the angles add up to less than 2 right angles.
I'm going to do maths on my banana next time I have one.
Okay, now we're going to move on to Euclid's parallel postulate. Deep stuff here, but very old. And it was number 29, apparently, to Euclid, and he proved 28 theorems before he needed to introduce this one. But actually, we usually call it his fifth postulate. I'm not sure why. So given any straight line, imagine it, close your eyes and think, given any straight line and a point not on it, there exists one and only one straight line which passes through that point and never intersects the first line, no matter how far they are extended. Got it?
Okay,
so okay, so that seems to be, has to be true. Can't imagine anything but a world in which that was true. But as you are not going to be surprised because of what we said earlier, it's only true in Euclidean geometry. It's not true in the other geometries.
If I were to say Euclidean geometry basically represents the world as flat in 2D, would that be no? Because it also includes 3D shapes, doesn't it?
Yes, but it's everything. Yes, but it.
If I were to generalize,
true. It's all about, but it's all about this postulate. It's all about the angles adding up to exactly 180 and parallel lines.
And parallel lines. Okay.
Yes. Okay. Now, for centuries, many mathematicians believed that this statement was not a postulate, but rather a theorem. And they spent hundreds of years trying to prove it as a theorem. And then finally, it was proved that it could, that part of the geometry which could be derived using only postulates 1 to 4 came to be known as absolute geometry. And then there's a bit more geometry that it really is a postulate. In other words, what these geometers proved was that you couldn't prove it from the other 28, and therefore it stood on its own as a postulate. Here you have what I think everybody was visualizing, which was the straight line through C and D, and the arrows mean, well, that's only a line segment. The arrows mean that you've got to imagine it going on forever. And as we've discussed before, the wonderful thing about mathematics is you can go to infinity, which you can't do in reality.
Yes, and that is the wonderful thing about math. You really can simulate infinity using mathematics.
So none of the blue line segments actually intersect the black line, but they would if you, as it were, produce them, if you drew them longer. The parallel is the red one. So there's only one parallel through E that never meets the line CD, even if you extend them both infinitely in both directions. And of course, we've got examples of parallel lines in railway tracks. Even if they were only slightly off the parallel, they'd meet sooner or later, and that would be a disaster for the railway train.
Literally.
Yes. Okay. Now, is the parallel postulate true in spherical geometry? Here we're looking at the geometry of on the surface of a sphere. And so what is the parallel postulate? Is given a line and a point not on the line, well, we ask how many lines can be drawn through the point that are parallel to the line. Well, there's only one in Euclidean geometry. So what about spherical geometry? It's false, actually, because as we talked about airlines on the globe, once you understand that the straight lines in the geometry are actually great circles, right? All the lines intersect each other, so there are no parallels
of the great circles.
Yes, but the lines
I'm not finished. You see the lines of latitude there; they don't seem to be intersecting each other.
No,
so...
but they're not straight lines. They're true circles. They're not straight lines because
So only
they
the great circles are straight lines.
exactly because the
Okay.
straight. So if you were in in London and you wanted to get to America, right? You wouldn't head along a line of latitude. You wouldn't head due west, would you?
Right. No. Yeah.
So the straight lines, you've got to remember that in spherical geometry, the straight lines are the great circles, and that's why from London to New York you go up above up towards the North Pole.
Okay, so you're following to take the shortest route, which is where you started off. You have to follow the great circle. Therefore, the only and that is kind of the definition of a straight line in spherical geometry. So if you're following a great circle, there are no parallel lines.
Exactly. To put it another way, in spherical geometry, the only straight lines, shortest distance between 2 points, the only straight lines are great circles.
Right. Okay.
So there are.
Yeah.
Okay. So there's no such thing as parallel lines in spherical geometry. So we think of parallel lines everywhere in our world, don't we? I mean, we make furniture and the edges are parallel. When we build the room, I look around, everything's parallel. Picture frames, edges are parallel. There's right angles at the corners. Most of what we make seems to be straight lines and parallel lines.
So what we manufacture is mostly Euclidean, but I bet there's no parallel lines on a banana.
Well, let's look at the hyperbolic geometry. Okay, Caroline, look at this picture. What does it tell you?
Okay, so let's see. Let me think what I've learned so far. We're looking for the shortest point, but the shortest path between two lines is going to be our straight line. Now, how do I know in hyperbolic geometry? Because I can visualize it on a sphere, but I can't even begin to visualize what's going on here, because you've told me that with those angels and devils, they were demons. They were actually all the same size. So I'm not even going to attempt it. I'm going to assume that the red line is a straight line.
They're all straight lines, Caroline.
They're all straight lines.
Yes, and let's introduce a different word, because I think it might help. You see, one of the problems in this conversation is the fact that we keep talking about lines and straight lines and curves that are really straight, and oh my goodness. So there's a word called geodesic. Okay. Now a geodesic, I think the geo in the root of the word there must mean something to do with the earth. Actually, I'm not quite sure.
Right.
I'm not a linguist, and desic must be something to do with design. But anyway, this is a mathematical word, and it means the shortest distance between 2 points is on a geodesic.
Okay, I'm going to write that down. Shortest distance between 2 points is on a geodesic. Okay, go ahead.
So L is the red one. Okay, L1, L2, and L3 are all geodesics. So they're straight in this geometry. And this is a model of hyperbolic geometry. And the straight lines, it turns out, if you do all the maths, which is quite complicated, the straight lines are arcs of circles, sort of Euclidean circles, that cut the outer circle at right angles. Look at those lines, the geodesics, L, L1.
Angles. Oh, okay. Wait a minute. Would it be correct to say that any 2 points on the circle, if joined by a line that's 30 degrees, would be so we could have a teeny weeny little, like between where L3 touches, we could have one just adjacent to it, as long as they're then 90 degrees,
Yes.
both, so that still would be not a straight line, it would be a geodesic.
Yes, and you see,
I'm definitely not comfortable using the word straight line with this.
so you see there a unit disk, which looks like a Euclidean circle, okay?
Yeah.
And you imagine the diameters. Now the diameters really do look straight to us because we've got Euclidean eyes, and they are also perpendicular to the edges. So
Right,
they are the exceptional geodesics in this geometry. Now, so right through the point P, not on the line L, right? Do those other lines cut the red line?
So is it true that parallel lines basically don't touch each other? I have no idea. I haven't a clue. It looks like it. Looks like it's true.
Going back to Euclidean geometry, there's only...
I can't believe I have Euclidean eyes, so I can't trust my eyes looking at this.
So if you have a straight line L and a point P not on L, in Euclidean geometry, there's only one line parallel to L through P. Right?
Okay, and is that L1?
No, not in this diagram, my dear, because this isn't Euclidean. I'm imagining, I'm saying...
Oh, sorry, Euclidean. Sorry.
Yeah.
I thought we were talking about this one, yeah.
But, oh, sorry. In in this geometry, so there are infinitely many lines through P that don't meet L. So there are infinitely many parallels that don't to L. So
in
in Euclidean geometry, there's only one parallel line through P, parallel to the line L. In spherical geometry, there are none.
None.
Because the great circles always intersect. And in hyperbolic geometry, there are infinitely many parallels.
I love it. Maths. Isn't maths amazing? It's like it all comes together in the end. It's brilliant.
We could have filled the rest of the day with talk about all these things. But...
Oh my goodness. But no, that was beautiful. Oh my goodness. I definitely learned something there. Now I've got to remember it. So see you next week. Thank you so much. Thank you, Toni. For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by Ainslie and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support Ainslie. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.